All right, guys. So what we have accomplished to this point is, in some sense, almost amazing, but we have developed a technique, a tactic, to avoiding having to go through all of the technical details. Find the derivative of a sum of two functions, a difference of two functions, or a product of two functions. The derivative of the sum is the sum of the derivatives, derivative of the difference is the difference of the derivatives, derivative of a product is that funky formula, carbon copy the second, derivative of the first, plus carbon copy the first, derivative of the second. It's a little funky, but it's almost amazing in that it allows you to compute the slopes of tangent lines for a function that you may not even be able to visualize concretely. Kind of cool. And then as you think about what we've done, we've got a formula to compute the derivative of addition, the derivative of subtraction, the derivative of multiplication. I mean, what naturally comes after multiplication? Well, the inverse operation of multiplication, division. So here's the goal for this video. Let's find the derivative of a function, which is itself a quotient of two functions. And let me preface what I'm about to do by saying this process is going to be cumbersome. Like, if you thought multiplication process got a little bit hairy in the details, this one's gonna get extra hairy. But, like, bear with me here, because once we go through the evidence to support this formula, we'll never have to go through the details again. The details will be done, they'll be in our back pocket, and we'll be able to move forward now with a formula to attack the derivative of a function when that function is a quotient. Okay, so let's go through the cumbersome details and go through it once and get it right so that we never have to do it again. Okay, we want to take the derivative of this function. How do you take the derivative of any function? You use the limit definition of the derivative. So the derivative that we are interested in with respect to this function is going to be, first, take your function, plug in x plus h. So here that's f of x plus h over g of x plus h. Subtract your function plugging in just x, excuse me. So that's f of x over g of x. And that's all going to be over h. And forgive me, I've failed to write in the limit. So let me write in here limit h approaches 0. Okay, now we want to deal with this limit. Note, within this limit, I mean, of course, you couldn't just plug in h equals 0 right now. You'd have 0 in the denominator. That wouldn't make any sense. So what we're going to do is deal with the fractions that are upstairs and add those together using a common denominator. So to do that, let's take the denominators, noticing we've got a g of x plus h and a g of x. I'm going to take this one on the right and multiply by g of x on top and bottom. And then the guy on the right, I'm going to multiply by g of x plus h on top and bottom. So what you in effect do here is give yourself a common denominator upstairs. So I tell you what, I'm going to write this below. Limit h approaches 0. This is all going to be over h because we're not dealing with the denominator just yet. But upstairs in the numerator, we've got f of x plus h, g of x, minus f of x, g of x plus h. And this is all over g of x plus h, g of x, the common denominator. So we've got this massively cumbersome expression. So be it. It is what it is. Let's work through it. Okay, so how are we going to work through it? In fact, we're going to employ a tactic that we saw last time, which was in this numerator expression, we are going to do nothing by adding something and subtracting that same something away. So what is the something that we're going to be adding and subtracting here? Actually, it's going to be very familiar to what we did last time. We're going to do f of x plus h, g of x, and now we are going to subtract f of x, g of x, and add in f of x, g of x. We still have the minus f of x, g of x plus h, because that doesn't go away. We still have the g of x plus h, g of x, because that doesn't go away. And in fact, we still have the h downstairs. And I tell you what, let's just deal with that h right now, because you know that when you divide by h, you're dividing by h over 1. And you know that whenever you divide by fractions, you could flip and multiply. So instead of dividing by h over 1, we could multiply by 1 over h, and if you multiplied by 1 over h, that would make the denominator g of x plus h, g of x times h. So let's just write it like that. Okay, so what have we done to this point? We've rearranged the expression that we originally wrote so that instead of having a double-decker fraction with an h downstairs, we've got the h properly expressed by multiplying by 1 over h, and we've also, instead of the numerator that we originally had, we subtracted f of x g of x and added in f of x g of x. So we've in effect done nothing, except re-express in a different form, and this form is going to be helpful to us. So what's the next step? Well, I'm going to do a couple things. One, if you view this expression as these two things in brackets added together, same tactic we've used before. Remember that, what, 4 plus 1 over 7 is 4/7 plus 1/7. We're going to employ that same tactic here to just break up the sum. So the first sum over the common denominator, g of x plus h, g of x times h, will then have added to it the second guy, which is g of x plus h, g of x, h. Okay, what's upstairs in each of these fractions? The first fraction is going to have what's in the first bracket upstairs. Note, in common is a g of x. So we've got g of x times f of x plus h minus f of x. Let me write that more clearly. Take out the g of x that's in common, you've got an f of x plus h minus f of x. In the second guy, note both of these have an f of x in common, and in fact, I'm going to factor out a minus f of x to help us out here. If I factor out a minus f of x, that's going to give me g of x plus h. And if I factor a minus f of x from a positive g of x, that's going to give me minus g of x. The reason for factoring out the minus f of x was just so that we had the standard expression for our derivative, g of x plus h minus g of x upstairs. And the long story short now at this point, I didn't express it, but we still have not yet taken our limit as h approaches 0, is if you look at the terms here, we've got a bunch of things being multiplied and a bunch of things being divided in both cases. If you rearrange, you can notice that in the first term, you've got an expression for the derivative of our function. F of x plus h minus f of x over h is the derivative of f. And in the second guy, if you rearrange and look at the terms there, you've got an expression for the derivative of g. G of x plus h minus g of x over h. So if you rewrite this out to be sort of more direct, ultimately, you've got the g of x over g of x plus h, g of x, but then that's just being multiplied by the derivative of f. The derivative of f was the f of x plus h minus f of x divided by h, the limit as h approaches 0. And then, what is added to on the right? Well, we've got a minus f of x. And I tell you what, just for simplicity, rather than writing plus and negative, let me just write a minus here. And then we've got f of x over g of x plus h, g of x times g prime. And now, at this point, check it out. We can let h go to 0 because we no longer have h in the denominator. Initially, we had h's in the denominator, and that wouldn't have made sense if we let h go to 0 at that point. But now that we no longer have just h in the denominator, we can let h go to 0. And you know that x plus h would become x plus 0, which is just x. And so whenever you look at the original, like the two terms being added together here, well, you've got a g of x and an f prime of x upstairs, because f prime of x is like f prime of x over 1, so that's in the top of your fraction. And what do you have downstairs? You've got a g of x times g of x. What is that? That's g of x squared, right? I mean, g of x times itself would be just g of x times itself. we've got a minus sign, and what do we have here? Well, we've got the g prime upstairs, because of course g prime is just g prime over 1. So upstairs we've got f of x times g prime. This is all over what's downstairs. We've got a g of x times a g of x. As the h went to 0, that first guy became g of x. So we got g of x times g of x. That's g of x squared. But then when you look at this expression, note you've got a common denominator in both cases, and you know what happens with the common denominator. You could add up over that common denominator. So the common denominator would be g of x squared, and what you'd have upstairs would be g of x times f prime of x minus f of x times g prime of x. And holy moly, that took a lot of work to get. That took a ton of algebra to manipulate the expression down to a point where it became digestible. But the big takeaway is, we computed the derivative for any function which is itself a quotient of two functions. You carbon copy the second function, you multiply by the derivative of the first function, you subtract a carbon copy of the first times the derivative of the second, and then you divide by a carbon copy of the second squared. My gosh, it's even a mouthful to say, it's cumbersome to write out, but the fact of the matter is, you now have the ability to compute the derivative of any function, which is itself a product of functions. And that's almost amazing when you think about it. And heck, in the next video, I'll go through some examples to see that in action.